Okay, cool. Hi, everybody. I'm Gareth. My project is building a zkApp staking pool on Mina. Okay, so let's take a quick look at the current status of kind of Mina staking pools. Where are we at? So there are a number of issues with the current setup. So delegators kind of have to trust that the validator calculated their rewards correctly. This can actually be a little opaque, particularly when we're dealing with supercharged rewards and how they're calculated. It's actually not that easy to validate this without running your own scripts. All rewards are custodied by the validator, who can stop paying or steal rewards. And unfortunately, we've seen examples of both of these where a pool has stopped paying rewards, and also in the delegation program where funds have actually been stolen. The pool payouts dominate the transaction throughput at the network, particularly at the start of an epoch. Now, this is clearly a lesser issue for kind of delegators, but for pool operators, it can actually be crazy slow to send all the rewards out, particularly for the larger pools who may be sending up to kind of 10,000 addresses. And it also kind of creates some congestion in the network, so it hampers other transactions getting included at those times. And I think when zkApps come to mainnet, we're going to see a bump in the transaction volume. I think this will become more of a prevalent issue. So what should a zkApp staking pool ideally look like? So firstly, anyone will be able to force a payout. So in this case, kind of the user would have to pay the transaction fees. So it would be expected in the normal case of operations, the pool operator kind of does this for you. But in the case of a pool not actually paying, we would be able to force it. It would verify that the payout calculation was performed as expected. It would ensure a validator cannot steal funds. I think this is probably the one most people care about. We can actually enforce this by requiring that the funds can only be sent from a zkApp via a valid proof, as opposed to using signatures. I think all of those above could kind of be categorized and just say they reduce the level of trust required in a validator, which is obviously a good thing. And finally, to reduce the number of payout transactions, ideally via batching account updates. Okay, so just on that last point there, one nice property of zkApps is that the account updates can actually be batched. That is kind of multiple account updates we can get into a single transaction. So what we can do right now is we can modify existing payout scripts with actually quite little effort to make use of this. So when using signatures, we actually don't even need the sending account to be a zkApp at all. And as we're using signatures, it's actually pretty quick to generate all of these. And we can batch kind of 10 account updates in a single transaction. So just using this, I've managed to fit 1,000 account updates in a single block on a prior version of Barclay. So this alone could kind of reduce payout transaction volume on mainnet by a factor of 10x if implemented. There's a very simple example linked in the GitHub repo there to show how it can be done. Okay, so batch sending is kind of like this really nice feature, but it's more of an improvement to the existing system. And we still have the issue with trusting the validator who's got to actually make the payouts. So to allow anyone to run the payouts, we obviously need to use proofs rather than signatures. We can still batch updates via proofs, and I managed to get 9 account updates, so slightly less, in a transaction with a single proof using a single approach. But we can split this kind of zkApp staking pool design problem into 2 distinct parts, which left and right here. So the first is kind of an Oracle problem where we need to get historical block data in order to calculate the payouts, because the daemon only stores the last 290 blocks, which is around typically like 19-20 hours worth of data. So in order to get like a whole epoch's worth of data, we need to get this from a different archive source. And then the second part of the problem is kind of once we have all the data and we can calculate the payouts, how do we actually process them? And I guess I've said we need to send via proofs so that anyone can run it, but we need to prevent someone making the same payout twice. And for the case of this project, I kind of examined 2 different ways we might do this. One is claiming rewards, and the other is via batch sending. So just quickly looking at the Oracle problem. I use the Mina Explorer GraphQL API, which I run, so it was quite handy to integrate, to provide the data required for determining the payouts. As part of the research, I also developed this really simple Oracle example and zkApp for the Foundation Delegation Program that checks to see whether the validator has correctly kind of sent back the rewards for the epoch. There's a little bit of sample output of an Oracle here. So the bottom there, the signature is what we're verifying within the zkApp itself. And essentially all we're doing in this example, we're checking that the amount sent is greater than the amount owed. And if so, we can send a transaction with an event that can subsequently be read back from the blockchain. Again, there's a link there to the repo. That runs as a AWS serverless function. And all it's doing is basically proxying the request to the GraphQL API, formatting it a little bit, signing it, and then returning it. So actually anyone could run that. Okay, so that's oracles. So now onto the case of like handling the account updates. How are we actually going to pay people? So I firstly looked into kind of claiming rewards. So if you've ever used a DeFi app, this is going to be super familiar, where you kind of go to a UI, click claim whatever time you want to in order to get your rewards. Kind of the main issue, obviously, with claiming is preventing multiple claims. And as we can't store everything in Mina state, we need to make use of a Merkle tree, as was discussed before. So we can use the Oracle to create this Merkle tree that we can store off chain. And then we have like an on-chain state variable that contains the root of the Merkle tree. And once the user claims, we can check the account is within the committed Merkle tree and then update the state with the new Merkle tree root. So I think that's a very familiar pattern, but the problem with this is it actually doesn't allow for concurrent state updates. So if multiple users try to claim in a single block, only the first is going to be valid and the rest are going to fail, which might be fine for certain applications, but for a larger application, and with Mina's kind of slowish block times, this really doesn't scale, as it's kind of inevitable for there to be multiple updates in a single block, and that's just a really bad UX. So kind of the next question is then, how do we handle concurrent updates? So there's a way around this using actions and reducers. And like really simple overview, with actions, you're sending a transaction which contains kind of some data in a sequence event, but we're not actually committing to anything, which kind of gets around these concurrency issues. So in this specific case, we'd probably send an identifier like the public key in the sequence event to indicate who's doing the claiming. And then in a separate process at a later time, it might be the next block, or you might wait until X many people have claimed. You can roll up all of these pending actions, essentially, which is the reducer step. And here we can take the similar approach, kind of using the Merkle tree, checking the accounts are in it, processing each action, and then but only updating kind of the Merkle tree on chain after all the pending actions have been applied. So this is actually a pretty good solution. I think it's going to be a very common pattern, but I don't think it's best suited for this specific use case. One thing today as well, it's not currently well supported on Barclay. Like there's no way to get the pending actions from a remote blockchain unless you're going to kind of roll your own solution. I guess it's coming soon, but currently this is what you'd have to do. You'd also need to be kind of running this reducer process all the time, and to reduce delays in terms of how often, or minimize the delay between when the user claims and when it's received, you'd have to run it for quite a high frequency for a popular app, maybe even like once a block, which would be potentially quite expensive in terms of fees, and also create a number of transactions that we're trying to avoid. I'll pause here because I see someone has got a question.
Hi, sorry for jumping in like this.
No worries.
I have two questions. One, so I'll start with the more boring one. You mentioned that you managed to fit 1,000 account updates into a block by batching. I assume that by batching you mean batching transactions, not batching method calls inside the transaction, right? Because it is my understanding that 10 is the actual account update limit for account updates per transaction.
Correct, yeah. So 10 updates and then 100 transactions in a block.
Ah, okay. So you actually batch transactions, not just operations inside the transaction. Okay, thanks. And second question would be, so your payout contract, is it the account that is actually receiving the rewards for the block production, or do you have to move the rewards to that account manually, or do you actually delegate the smart contract that runs the payouts as well?
Yeah, if I understand your question correctly, what you would do is the zkApp would be the Coinbase receiver. So it would accrue all of the block rewards itself.
Yes, that's it. Thanks.
Cool. Thanks for the questions. Okay, just a few slides left. So actually, rather than that claiming approach, I went for a batch sending approach where basically we're kind of just sending all the rewards to the delegators at a set frequency. I've just chosen once per epoch, as that's pretty familiar to what most people are doing currently. So some advantages to this, it's already the way it happens, so it's quite intuitive for existing delegators. We don't have to deal with any compounding issues or accumulating funds. You can imagine a larger pool could become quite a honeypot for potential hackers. We can optimize for the number of account updates that can fit into a transaction rather than, say, waiting on there to be 9 claims or whatever before processing. We don't need this reducer process running continuously. If you imagine you're sending once every 2 weeks and you can batch send them in a couple of hours, you don't really have to do anything for the rest of the 2 weeks. And finally, it's kind of, there's just less complexity and overhead than actions of reducers. And as I finish with slides, I'll stop again for a question.
Yeah, hi again. How do you deal with like precision issues in terms of math? So I assume you have your delegator, right? I don't know what is like the life cycle for delegation here, or do you like have to lock your delegation or whatever, but that is not important. So imagine you have a reward of, I don't know, 100 Mina that you need to distribute in a certain cycle, and you have a bunch of people who are delegating to you, therefore they are supposed to receive a part of that reward, right? So proportionally, depending on how much they delegated, etc., like we all know how that works. But how do you deal with rounding errors? Like what we've seen or what we've done before with contracts and math is that we multiply the numbers to some crazy values, like 10 to the power of 24, or I don't know, so that all the math errors, like the overflows or the floating points, will be a number that's not relevant, let's say, like too small or something. So that's how we dealt with rounding errors. I don't know, how do you do it, or if it's even applicable here?
Yeah, it's definitely applicable. There's a little note to this on my last slide, so you just preempted it. But essentially, at the moment, I'm handling it all in the Oracle end. So I don't really have to worry about that, in the sense of we already have existing payout scripts that do this, and we just use a rounding, basically rounding to the 9th decimal place kind of thing. But it's all being handled in the Oracle as opposed to in the zkApp currently.
Can you please share your slides as well so we can take a look at them?
Yeah, absolutely. Alrighty, so finally, so how can we actually create a zkApp to perform these batch payouts? And I think this probably answers your question here in terms of the rewards here. So what we'll do is we'll effectively implement a sequencer, but we'll use the Oracle to enforce the sequence. So here's some sample output from the Oracle in the data below. So there it shows you the rewards, but it also shows the index here, which is 0 in this case. So this is actually a pretty straightforward implementation. And the zkApp firstly gets the data from the Oracle and validates the signature. We store the current index and epoch on chain as state variables, so that basically we can assert within the zkApp that we are processing the correct index, and we're just incrementing the index every time. We make a batch of account updates and update the on-chain state to the new index after all of these account updates have been applied. So you basically just continue this until all the payouts are being completed for an epoch. One thing we do also need to do is enforce that we can only run this once per epoch. Again, we can kind of just pass that off to the Oracle and say, is this being confirmed? Or we could commit to, say, a minimum global slot number. So in this case, we're doing epoch 39, so we could say, this can't be processed until, say, slot 1000 of epoch 40. Okay, so finally, after kind of all the payouts have been completed for an epoch, we actually then need to pay the validator their fees for running the block production nodes, and also then to basically bump everything so we can start the next epoch when it's ready. So we can do this by creating a second method that completes the epoch. I've added some comments here to kind of indicate how this will work. So in doing so, we validate the Oracle signature as we did before. We assert that the current on-chain state is equal to the number of delegators for the epoch. Again, we can just get that data from the Oracle. This just basically shows that we've actually paid everyone. We then send the payout to the pool operator. Here we can actually use on-chain state variables again for the public key, say, of the address to send to, but also the fee, which kind of has this nice effect that the fee data is actually now visible on-chain and transparent, as opposed to kind of hidden behind a private service as it is now. We then kind of update the chain state to increment the epoch and reset the index to 0 again, such that once the next epoch is kind of ready, we can just keep going in this fashion, incrementing every time. So finally, next steps is a fully working proof of concept on Barclay. I've still got a few niggles to iron out. Then kind of investigate moving more of the logic into the zkApp. This is basically what we were discussing earlier. It's quite reliant on the Oracle. So while anyone can kind of view and reproduce this data, I'd like to see how much more of this I can kind of do from within the zkApp itself. The next is kind of to investigate multiple data sources to reduce reliance on a single Oracle. Kind of as above, we're so reliant on the Oracle here, and as a result, kind of Oracle attacks would be possible on this type of system. And looking to collaborate to bring a system or something like it into production. And that's my contact details on Discord, and that's it. Thank you.